Thank you very much, Arnold, and thank you to the AIBC COVID Work Group for organizing this session or this webinar and inviting me. But mostly, thank you to the participants and who are taking the time to join in this discussion today. You're the most important people here. As Arnold said, and as the slide says, I'm talking about the role of building ventilation in infectious aerosol transport inside buildings. I want to start out with a very, very quick disclaimer and that I'm an engineer. I'm not a virologist or a microbiologist or any kind of biologist. I really don't have the expertise to talk about, health issues and so on. So I'll talk about what I know about, and I'll stay away from the many, many things that I don't know about. So what am I going to talk about today? I'm going to talk about the airflows in buildings that we care in the context of, that we care about in the context of indoor aerosol transport, and a little bit about their magnitudes. And then I'm going to talk about how you can use airflow and ventilation to control or reduce aerosol exposure. And then I'll talk a little bit about some of the suggestions that are being offered by various bodies to use ventilation and airflow to reduce, the risk of indoor viral transmission. And then I'll wrap it up, and we can move on to the next speaker. I want to start out with a few key concepts. The first being, ventilation, and I've displayed here the definition of ventilation that you'll find in ASHRAE standard 62.1, and it's about treating air and delivering air. And it's interesting to note that this definition says nothing about outdoor air. It's implied, when we talk about controlling contaminant levels in buildings, because outdoor air is a good way to control contaminants that are generated inside, but the definition itself doesn't mention outdoor air. And this is important because people use this term differently. Some people, when they hear ventilation, they think outdoor air delivery. Others think about air delivered to a space to heat and cool, to deal with thermal load. So it's really important to to speak and write clearly, right? And I'm going to try to do that. And so I'm sort of setting the stage, to introduce some of these concepts. So, and the other thing I want to mention is that the ventilation requirements in ASHRAE standard 62.1 were not developed with infectious disease transmission in mind. That topic was discussed, by the committee, but those numbers are not, developed, in order to control airborne disease transmission. I also want to point out or remind many of you that every building is different. There are no typical buildings there, and I'll talk a little bit more about that more later on. Buildings leak. The skins of buildings, the exterior envelopes leak air between inside and outside. They can be designed and constructed such that leakage is low, but in general, even in a tight building, there will be some leakage between indoor and outdoors. And if you want to understand the airflow in a building, you need to, acknowledge that leakage and deal with it. When air moves into a building or within a building, it does so, based on what the physics tell it. It's the air sees a hole and it sees a pressure difference, and it moves accordingly. It doesn't, it doesn't matter, it's, so much what the architect and the engineers say, their design intent is displayed here on the slide. Hopefully, the way the building is built and installed and operated, results in the design intent actually being achieved, but the air doesn't know that. Air only knows physics, and many buildings operate quite differently from the way they're designed. And I say that, based on studying, and reading about airflow and ventilation research in buildings, but I acknowledge that the number of buildings where we, as a research community, have looked at airflow is really, really small. And we've learned a lot from those studies, but it's really hard to generalize to the building population at large. Again, every building is different. I'm almost done with these, my diatribes here. We hear a lot about fresh air, and that's great, I guess, if you're in, some beautiful mountain location, but a lot of outdoor air is not fresh, and whether it's particles or ozone or other contaminants. So it's, for for honesty's sake, it's better to call it outdoor air than fresh air unless you're sure it's fresh. And then finally, one air change an hour is really just a unit. It doesn't mean all the air in the building or the room is replaced every hour. It means that a volume of air equal to the room or the building enters. But once it enters, it mixes with the interior air, and the air that leaves is a mixture of new air and old air. So it's not all replaced in an hour. It's really replaced at an exponential rate. And we can talk about that more later on if there are questions. So which airflows do we care about? Here is a ventilated space with a high-risk occupant. And I'll show a few of the, in the schematics, I'll highlight some of the airflows we care about. So I just displayed here this mechanical ventilation system, which is really more typical of US systems. There are different approaches in Europe and other parts of the world, but basically the air is brought in, it goes through a filter, a fan delivers it to the space, and then the air is pulled back from the space in many systems. Some of it might be recirculated, filtered again, the rest might be dumped out. So this is intended to represent a central mechanical system, again, typical of what you would see in North America. This little diagram here is a simpler ventilation system, which just might be a hole in the wall with a fan and a duct. I show a filter. Hopefully that air is filtered. It certainly should be, given what goes on outside. And so this is meant to represent a very simple mechanical ventilation system. Next, we have infiltration. I mentioned how buildings are typically leaky, and unless you've verified that they're not. So this is airflow into and out of a building through unintentional leaks, cracks around windows and other interfaces in a building. And this air is, it's uncontrolled, it's unfiltered, it comes in where it wants and it leaves where it wants. It's not a good way to ventilate a building in terms of indoor air quality and energy and control. And ideally, you want to reduce the infiltration. Natural ventilation is airflow into and out of a building. It's also like infiltration, it's driven by weather and the operation of certain appliances and equipment in the building. But natural ventilation occurs through intentional openings, like windows or more elaborate designed natural ventilation systems. Another airflow that is important is our local exhausts, and I'm showing this in a hood, a cooking hood over a stovetop. The idea, and you'll see these in toilet rooms and other places. The idea of local exhaust is to get the odors and the contaminants out of the building before they have an opportunity to mix with the rest of the building. And then the last airflow I want to mention are the airflows through local filtration systems or portable air cleaners that we're hearing a lot about today. So these are the airflows we're talking about, and each one has its own story, and maybe we'll hear about some of them later on. This slide just shows some of the magnitudes of these flows, but there really isn't time to talk about these during this presentation, but there they are nonetheless. The other airflow I want to mention are interzone airflows. The airflows, from one zone of the building to another zone of the building. In residential buildings, this picture is also very US centric, but we have basements and attics and crawl spaces and all sorts of places, volumes of air in the building that can exchange air with the living space. And then in commercial buildings, it's more complicated. We might have stairwells and elevator shafts and mechanical rooms. In general, the magnitude of these interzone airflows are similar to the airflows you might see between indoors and out. I made this point before, and I just wanted to stress that buildings are very different. I show the number here for the US, how many millions of buildings we have in terms of dwellings and commercial buildings. And worldwide, the numbers are obviously much, much bigger. And they are different, and the differences matter in terms of how the building is laid out, how the ventilation system is designed, what the occupants are doing. And I mentioned earlier that we've studied ventilation and airflow in a very, very tiny fraction of buildings, a non-representative fraction. So we know what we know from those buildings, but we really don't know very well in a more statistically valid sense. And then, the number of buildings where we've studied the impact of ventilation on aerosol transport is even smaller. So, what can you do with airflow to reduce aerosol exposure? And this slide, I originally created it with respect to outdoor aerosols. The first thing you can do is build the building tight and ventilate it right. People have been saying that since the 1980s, and I added filter to the ventilation concept. You can overpressure buildings to keep the outdoor aerosols from infiltrating, and that's a good concept, but you have to be very careful with moisture management when you do that. The third concept is to manage your airflows and your pressures so that the air within the building flows from clean spaces to dirty spaces. And I think our speaker, Ali Reza is going to talk about that concept in much more detail. And then finally, commissioning, operations, and maintenance. You may have a great design, but it's got to be installed. You got to check on the installation through commissioning. It's got to be well operated and maintained to achieve, what you designed it to do. And then the last point here is that ventilation will only get you so far if you have a strong local source. If you have an open can of paint in the room, you're not going to solve that with ventilation. If you have a unmasked, ill, coughing person in the room, you're not going to solve that with ventilation. You got to deal with the source, either ideally get it out of the space or do something else. There are a number of organizations that have been making recommendations related to ventilation for reopening buildings, and here's just a few that are listed here. There's a lot more. And these are some of the topics that are covered. And I'm just going to comment on some of these, not all of them. That's a longer day. So we hear about increasing outdoor air ventilation. I mean, that's a good idea. It has many advantages we knew before the pandemic, but you've got to do it. Your system has to be able to do it, and not just move that much air, but it also has to be able to cool or dehumidify that much air. And you also have to think about the outdoor air quality when you do this. So there's some caveats here. It can be helpful, but not every system, is able to bump up the outdoor air intake sufficiently. More efficient filtration, that helps too. But again, you got to look at what your system can handle, in terms of the pressure drop through the filter. You want to make sure the filter is well sealed, and that you have a maintenance program so these filters get inspected and changed on a regular basis, which reminds me I need to change my furnace filter. I'll do that soon. Some folks have advocated changing relative humidity. I'm not an expert in this area. I don't know if we know the right number, but humidifying buildings, adding moisture to buildings can be a risky proposition, and you have to be very careful if you're going to do that. And there are many people who would suggest it could be ill-advised, and it's not the first thing you want to do. Opening windows, that's open windows are great, connect you to the outdoors. It's, psychologically that's good, but what is the outdoor air quality? What about moisture and noise and security? And just because you open a window doesn't mean the air is going to come in. It may go out. How much air is going to move? Where it goes within the building are affected by the overall pressure dynamics. And then the last recommendation is to change the air distribution system in a building. And that's a big it can be a big cost, and it's limited in terms of what you can afford and how quickly you can do it. And so to wrap up, the first point is do no harm. Don't change the ventilation system unless you understand it, because you could make things worse. Good ventilation of buildings has always been important. And, I think now we're realizing it's even more important. This is a great time to check out your system. I have a link to the ASHRAE guidance from the Epidemic Task Force, and also a nice short article that Larry Schoen wrote about operating buildings during the pandemic. And then the last thing I'll mention is an online tool that NIST has developed for doing some single zone analysis to look at the impacts of ventilation filtration and so on indoor aerosol transport. So with that, I am done, and I'm remembering that I need to introduce the next speaker, Kath Noakes from the University of Leeds in the UK, who's a friend and a colleague, and I know she has some very interesting things to say, so I look forward to hearing them. So thank you very much.